Hello everyone, we are Group 2 and I'm Danting. Our topic is biomimetic materials. This is our outline today. I'm going to firstly briefly introduce biomimetic materials, and then Gigi, Shikong, and Jabe will focus on these three different advanced biomimetic materials. Last, Changtai will do a summary. So for the introduction, let's first look at what biomimetic materials means. Biomimetics or biomimicry is the emulation of the models, systems, and elements of nature for the purpose of solving complex human problems. Actually, compared with existing engineering materials, natural materials are more multifunctional, more eco-friendly, with higher mechanical properties, and perhaps the most important one, they are simpler in composition but more efficient in performance. This means they have weak constituents, but they can create excellent properties. All of those advantages are what we can learn from the natural materials. Next, I will introduce two small examples. So the left one is the lotus leaves. As you can see, it has a very hydrophobic surface, and by researching its mechanism, namely the lotus effect, nowadays lotus effect is applied in many areas, such as self-cleaning, waterproofing techniques, oil and water mixture separation, and so on. The red one is the spider silk. It attracts lots of interest because it is a kind of lightweight biological materials with both high strength and high toughness. It's recently become clear that its outstanding mechanical properties are mainly due to its structure, and it is possible to construct a kind of lightweight, strong, and tough artificial fiber like it. Next, welcome Gigi to introduce the super hydrophobic coating with super robustness against abrasion expelled from mosquitoes' eyes.
Hello everyone, my name is Gigi, and in this part I will give you one example of biomimetic materials. In this case, a mosquito eye like super hydrophobic coatings with super robustness against abrasions. As we all know, harsh environment is very dangerous to our materials. For example, here acidic environment can cause corrosions. So protection is needed, and in this case, super hydrophobic coatings can be used to metal protection against harsh environment such as corrosions. This property can be achieved by organizing the surface with a nanoscale structure. However, this one have a drawbacks. Now the surface become vulnerable to abrasions. Mosquito compound eye has microscale hemispherical structures, and if we further magnify the eye, we can see here nanoscale papillae with tight arrangements. So inspired by these unique structures, materials with super ability to resist abrasions as well as possess a good mechanical properties can be fabricated. To begin with, aluminum is anodized by using a DC voltage to create anodized aluminum oxides nanoframeworks. These nanoporous frameworks is then coated by PFDS titanium dioxide hybrid solder, and the result is shown here. So now our substrate is protected by a layer with a thickness of coating is around 50 micrometers, with titanium dioxide nanoparticle filled deep porous up to a depth of 15 micrometers. The anodic aluminum oxide has outstanding high hardness property and excellent abrasion resistance. Meanwhile, PFDS titanium dioxide is super hydrophobic. So this combination is expected to result in a material with super robustness property against abrasions and at the same time has high water contact angle value. From the abrasion test, we can see the sample has high robustness to abrasion performance. The sample able to maintain its low wetting state despite the thickness loss up to around 15 micrometers. Now, there is a significant change to the water contact angle value after coating loss more than this value. The reason is that the filler PFDs titanium dioxide only fill the sample up to a depth of 15 micrometers, meaning more loss than that value will result to this filler diminish and we will only have the AAO here. In addition, figure hardness test is also conducted to obtain the surface hardness database sample. The tests show a promising result with a value of 428 here, which is this value far beyond industrial aluminum alloy standard, which is around 200. So, in conclusions, by biomimicking mosquito compound I, we can fabricate material with ability to withstand against harsh environments. Moreover, the result open feature opportunity and possible enhancing other type of materials such as titanium.
Hello, my name is Jikong, and I'll cover the area of eggshell membranes. So, what are the functions of the eggshell? Eggshell structure forms an baryonic chamber for the developing chick, providing mechanical protection and a controlled gas exchange medium. It is also a container for the egg, providing protection of its content and even for the antibacterial function. Eggshell structure usually consists of several main parts: albumen, eggshell membranes, calcified eggshell, and cuticle. The major composition in eggshell is about 96% calcium carbonate to provide the mechanical support. The rest of parts includes 2.5% organic matrix together with magnesium, phosphorus, and various trace elements. The organic matrix is the most important component of the eggshell. It involves the process of eggshell calcification, directly affects the mechanical property of the eggshell. Additionally, some eggshell matrix proteins have antibacterial effects. Referring to this table as an example, a couple of typical proteins are shown. Calcite and proteins in eggshell interacts with minerals to control its structural organization, thus determine its mechanical behavior. The shell is the source of calcium for chickbone mineralization. Eggshell is the fastest in calcium carbonate biomineralization with excellent mechanical properties. Eggshell has an intensive structural functions and combination of mechanical properties, which must be rigid and stiff, but while hatching, the chick will break out using its own beak. In chicken eggshell, mineral layer is about 0.3 mm thickness that can withstand a static pressure of more than 3 kg. Eggshell has a low fracture toughness of 0.3 megapascal and a high Young modulus of about 55 gigapascal. The Young modulus is impressively almost 3 times higher than the bone. Eggshell membrane is a potential bioresource that can be engineered for a variety of applications. Considering its abundant and unique property made it suitable for state-of-the-art application. Let's take a look. Applications are split into categories. In electrical devices, we have battery as potential alternative to lithium-ion. Capacitor generally made from carbon-based materials can be toxic. In this case, ESM can be used as separators between electrodes. Then there is solar cells, semicons, and fuel cells. ESM is also suitable for sensor fabrication as a detector for glucose, chemical compounds, and even to detect pesticides. In environmental engineering, ESM absorbent can be used to absorb heavy metals or even as a sorbent. Due to its low toxicity and biocompatibility, soluble eggshell protein in biomedical engineering is suitable for cell culture. ESM could also be used as biological dressing for burn or skin grafts. Presently, ESM-based products are commercially unavailable, but under a different label, natural eggshell membrane is accessible in the market. Thank you.
Hello, my name is Guo Jiabei, and I'm gonna introduce methyl-inspired materials, including a brief introduction of the moisture adhesion of methyls and some important applications in adhesives. In the technology of adhesive bonding, water or moisture has traditionally been treated as a surface contaminant or weak boundary layer. However, there are many organisms in nature that can adhere firmly underwater, such as methyls. Muscles attached to solid surfaces in the sea. Their adhesion must be rapid, strong, and tough, or else they will be dislodged and dashed to pieces by the next incoming wave. Their adhesion towards many surfaces using muscle-based proteins, and they can be secreted from the base of its foot filaments as shown here, which are enriched with dopa. This protein has advantages of water resistance, high strength, and excellent toughness. As shown in this formula, the catechol groups in dopa provide superior underwater adhesion, and diverse interaction mechanisms can also be created by dopa with its surroundings, such as gelatin, metal coordination, and ketone-pi interaction, and so on. So therefore, it is important to mimic the underwater adhesion mechanism of muscles. So the common approach for mesomimetic design is to introduce catechol functional groups into a native hydrogel material, and the constructed polymeric materials have high strength, toughness, and are available as self-healing adhesives for biomedical applications or other engineering fields. The figures show two common examples, chemical structures of dopa-modified PEGs and the design of cationic adhesive polymers, which have better biocompatibility and underwater adhesion respectively. Here shows a study of mesomimetic double cross-linked bioadhesive. In this study, dopamine was grafted onto the gelatin backbone to impart the adhesion ability of the catechol group. This triggered cross-linking by complexation of the catechol group and synergized with other cross-linking to ensure long-lasting adhesion with good biocompatibility, biodegradability, and elasticity to be used for biological internal tissue adhesion and sealing. To summarize, progresses have now been achieved in the research of smart meso adhesives with adjustable temperature and pH responses, which makes them valuable for a wider engineering field.
Hello, my name is Chang Tai. In this part, I will give a summary. The three materials mentioned above are inspired by different organisms and used in different fields, but they are all bio-inspired materials. This shows that the biomimetics has gained a firm foothold in material research and can meet the needs of new material research and development in different fields. However, the structure of natural organisms is complex. Not every feature serves an effective purpose. Therefore, it is an important part of biomimetics to accurately decide the effective feature and mechanism of organisms. In biomimetics, the selection and combination of materials are also diverse. Sometimes varied materials are required to be used in combination to obtain the target effect. For example, the mosquito eye-like coating fabrication. Sometimes different materials can be used to achieve the same purpose, like the variety of methods to imitate muscle adhesives. Future research directions remain to address how to accurately find and replicate key features of organisms with suitable materials for commercial production. Self-assembly and synthetic biology are expected to be the future research technologies of biomimetics. Small-scale elements are assembled into larger structures through self-assembly that enable control over the physical properties of the material in multiple scales. Synthetic biology can produce biomimetic materials by controlling microorganisms or artificial cells through programming their DNA. The evolution of nature has created various structures and mechanisms suitable for different environmental conditions. Exploring and using those inspirations from nature will lead to the progress of human science and technology. The influence of biomimetics will penetrate various fields to benefit our production and life. Finally, our imitation of nature will continue. Biomimetics and nature will lead us forward. That's all content of our presentation. Thanks for your listening.